Z-solvers. Why is this actually desirable? Well, Z-solvers are, yes, even much more efficient than QBF solvers. This whole research field of QBF is quite a young research field, and Z-solvers have been there for, I don't know, quite a while, like 15 years since they become really efficient. So Z-solvers, I guess, are much more mature engines with more optimizations, and QBF is a rather young discipline, but I guess that in the coming 5–10 years QBF solvers will catch up, and there will be no point in implementing this algorithm with Z solvers anymore, but the QBF solvers are so efficient that this is much more clever. Nevertheless, let's think a little bit how we can implement this algorithm now with plain Z solvers. I also want to do this on the blackboard. Is this fine, or is it better to turn on the... Oh, let's turn on both. Even better. Okay. The algorithm we are going to develop contains a lot of ifs and elses nested into each other, so I will draw it as a tree rather than an algorithm. The first step we do is an initialization step, basically. As usual, we start by saying our first version of the winning region is simply the set of all states. In addition to that, I will use a formula which I call U. And this formula U is a formula over the state bits and the input bits. I will talk about this formula U later. For now, you can safely ignore it. We will initialize it to true, and this will help you ignoring it in the coming formulas. Now, the next step, the first real step, is we ask a set solver the following question. And I need some space here. Is it satisfiable that we can find a state which is, let's add this U first, but ignore it. Can we find a state which is in W and we take a transition which is allowed by our transition relation, and what else? We end up in a state which is not in W. So, let me illustrate this graphically. We have our state space again. We have our current version of the winning region, which is initially just a set of all safe states. And what we are asking the solver now is there a state, let's call it x1, such that from this state the evil environment can find some input, let's call it I1, such that the system player can find some output, let's call it O1, such that we end up in a state x1 prime. And this x1 prime is outside of W, but x is inside of W. So basically this query just asks whether there is some transition from inside of W to outside of W with some values for the inputs and some values for the outputs. Ignore this U part here. Now, as before, this solver returns either sat or unsat in this variable sat, let's say. But in case of satisfiability, it also gives us a satisfying assignment for basically everything. It gives us a concrete state, x1, we named it here, a concrete input I1, and a concrete output O1, and a concrete next state x1 prime, which satisfies this super cool formula. Good. Now there are two different possibilities. This call can say sat or unsat. Let's do the easy case first. Let's first make it smaller. If this call is unsat, then this basically means that actually there is no way for the evil environment to leave W, because there is no transition that leads from inside of W to outside of W. And this basically means that we are done with our algorithm, just like before, and can return W as our resulting winning region. The more interesting case is when this formula is satisfiable, so our sat solver says yes, there is one transition which leads from inside of the winning region to outside of the winning region. What does this actually tell us? Not much, right?
Not so much, because we have all outputs, so probably there's still a choice of output which would not lead
Exactly.
outside.
And this is exactly what the algorithm checks next. Next, we check whether A is satisfiable, that from the state x1, which we computed in the previous step, and the input with the input I1, we can take a transition, maybe with some other O, such that the next state is actually in the winning region. So what this formula asks is, basically, we say the state x1 and the input x1 is fixed, but can we find maybe a different output, different from O1, such that we do not fall out of the winning region? So the question is there some other O, let's call it O2, such that we end up in another state, x2 prime, which is actually inside the winning region. This is what this formula asks. Now, what we get as a result is, again, an answer satisfiable or not. We already fixed the state to x1, so this call will give us x1 again, which is not really interesting, and we also fixed I1 as an input, so we will get exactly this input again, but we may now get a different output. I call it O2, namely an output which leads to another state, which is called x2 prime here, such that this formula here is satisfied. Again, there are two possible answers we could encounter. Let me see how I have to draw it. The sat case left, sat or not sat. Let's make the sat case first. What does this mean if this formula is really satisfiable? So what we tried now is, first we tried to find a transition which leads outside of the winning region, and then we found another output we could give in order to avoid falling out of the winning region. What does it mean if such an output O2 exists, such that we avoid falling out of the transition relation?
So that it is actually in the winning region, and therefore we don't want to check it again, and therefore we add a new.
Perfect. So this really means that the evil environment here tries to break out of the winning region. But from this state x1, with this input I1, it cannot break out of the winning region because the system can find some O2 such that it avoids that we get out of this winning region. And that's why the only thing this tells us is that the evil environment cannot fall out of the winning, cannot get out of the winning region with x1 and I1. So we better should not try this particular x1 and this particular I1 again when we do this check in 2. And this we make by saying we update U which is a formula over x and y. This is the old u and not x1 and I1. And then we go to step 2 again. By going here, the subsolver will then try to find another way to fall out of the winning region, but this one way, namely x1, I1, we have already excluded by saying this is not part of u anymore, and this formula here must satisfy u. So at least we made some progress. This subsolver which tries to break out of the winning region has now found out that this does not work, and it will try another possibility in the next iteration. So this was the SAT case. Let's also continue with the unsat case. Unsat means, in the first call, we found a state x1 and an input I1, but now we cannot find any output such that we get back into our winning region. What does this tell us?
We have to exclude the xy state.
Exactly. So this is really a problematic state, because if we are in this state, then the evil environment can just pick I1 and then we are doomed. We cannot find any O2 to go back. This way is really a way for the environment to enforce leaving the winning region. So this state is lost and we must exclude it from our winning region. So I write it like this. Here we already know exclude x1 from W. But we do not do it straight away, because one thing we should still check, so we are going to exclude this state x1 from the winning region, but before we do this we should check whether this is actually an initial state. Because if this is an initial state, then we can stop. We know that our specification is unrealizable and we can abort, just as we did before. So the next question we are going to answer, let's name this 3 and this 4. In 4 we actually ask whether, let's also write it like this, is it satisfiable x1 and the formula characterizing our set of initial states. Now this can also be implemented a little bit more efficient than with a core to a subsolver, because if this is a complete assignment to all the state variables, we can just insert it into this formula and just check whether it evaluates to true or false. Or even simpler, if I is not a set of initial states but only exactly one initial state, then we can just syntactically check whether these two are the same. Still, we can get 2 different answers, namely if yes, then we know that we just excluded an initial state, which means that our specification is unrealizable. Otherwise, if this is not satisfiable, then we do what we already knew what we need to do here. Namely, we update our formula W by being the old formula W and not x1. Because from this state x1, the evil environment can pick I1, and then we have no choice to pick any u such that we go back to the winning region, so we are really forced to leave the winning region. So x1 is bad, it needs to be excluded from the winning region, and this is just what we do here. There is another subtle thing. When we change our winning region, we also have to reset our u to true. And then go to step 2 again. Why do we have to reset our u? Well, we have our winning region. Now when we update our winning region by cutting away a certain part, which is this part here, it may not be able to leave the winning region from this state before, but if we reduce the size of the winning region, then it may actually be possible to leave the winning region from this state here by going there. This is why we have to throw away everything we have learned about things that are not helpful for leaving the winning region. Because if the winning region shrinks, then we have more possibilities for states to go into. Because as soon as W shrinks, not W grows. And we have more possibilities to go into some other W we did not have before. That's why we have to reset our set U in this case. This is just a subtle thing and not so important for understanding the basic idea of the algorithm. It is important for the performance of the algorithm though. Okay, so this was actually, I think, the entire thing. Questions so far?
This is faster than the QVF based approach.
It's surprising, but so this alone is not really clever. Let's talk about this a little bit. So here you have the same algorithm written with a lot of ifs and else instead of such a tree, and also a lot of explanations which tell you exactly what we have drawn here on the blackboard, just for future reference. But the algorithm, as we've just discussed it here on the blackboard, is not so super efficient, because one thing we really need to do is, before we exclude any state from the winning region, we again generalize it into a larger region of states that is excluded. And the same trick we also apply for updating U. Also, in this step here, where we exclude a certain state input pair from our set U, also here we generalize it into a larger set of state input pairs that should not be tried again. With the same trick we have already discussed before, namely dropping variables from our satisfying assignment. Other optimizations that can be applied to this algorithm is, we do not really have to reset this U each and every time, but we can do this lazily with some heuristics. Also, we do not really have to update the negation of this next state copy of the winning region in this complicated formula each and every time. We can also update this formula only lazily, work with the same formula, although we already know that it is outdated, and only if we find out that nothing works anymore, then we update the formula and try again. So this is the basic idea of updating all these formulas just lazily. This improves the performance quite a lot. Also, here we can apply something which is called incremental SAT solving. What is incremental SAT solving? Usually, when you have a problem and you apply a SAT solver, then often you solve very similar formulas again and again. So also for our formulas here, the formulas always look almost exactly the same. There's just one additional clause maybe here and there. And modern SAT solvers can exploit this by so-called incremental SAT solving. They keep all the information they have learned so far and try to find a solution of the updated formula, because most probably it's very similar to the solution it has already given before. So this is the idea of incremental SAT solving. Do not throw away anything you have learned for previous course to the SAT solver, but use all the information you have already learned for next course to the SAT solvers. This is what makes this approach efficient. Unfortunately, there is no such thing as incremental QBF solving yet, because this is much more complicated to realize, and this may also be a reason why the SAT solving based approach is more efficient than the QBF based approach, although it contains much more iterations usually. So when we compare the advantages and the disadvantages, we can say that here we only need SAT solver cores and no QBF solver cores. These SAT solver cores are usually much more efficient than QBF solver cores. Also the formulas are quite small here, just like before, but the main disadvantage is that here you really may need millions of cores to these subsolvers, but they are usually super fast. So for one benchmark, this AMBA benchmark, which you also have in your benchmark framework, it's roughly like this. This first approach, which we discussed, would require like 10 cores to a QBF solver, because also the BDD-based implementation would require exactly 10 iterations to solve the problem. The QBF-based learning approach requires around 1,000 cores to the QBF solver, and this approach here, I think, requires several millions of cores to the set solver, but they are so super fast that this is done in a few seconds. But we will discuss some experimental results a little bit later. I only have one more completely different synthesis approach, which I want to briefly discuss, just with 2 slides or so. Here the idea is completely different. When we take a step back, then what we actually need to find is a winning region. A winning region is just a set of states, usually represented as a formula W over our state bits. So we need to find a formula over our state bits, and this formula has to satisfy 3 properties. First of all, every initial state has to be contained in this winning region, which basically just means that the I formula must imply the W formula. Or graphically, the I region must be contained in the W region. Next, every state of the winning region must also be a safe state, so this implication here must hold. Or graphically, the W region must be fully contained in this region of safe states. And the third and most important property is, whenever we are in a state of the winning region, then we must be able to enforce to reach a state of the winning region also in the next step. This is what makes this winning region W here inductive. If we are here, then we can also go there in the next step and go there in the next step, so we can always stay in this winning region W. So these are the 3 properties that must be satisfied. So our goal is now to find a formula, W, over the x variables, which satisfies these 3 properties. Now this is not a simple task, but we can apply a trick in order to do this. We can define a parameterized function over the state bits. Here we introduce additional Boolean variables, named k here. They represent basically our parameters for the template, and when we fix concrete values for these k variables, then we get a concrete function over our state bits. If we fix different values here, then we get a different function over the state bits. This way we can reduce the search for such a function over the state bits to a search for concrete values for our parameters, basically. All we need to do now is we need to find template parameters such that our 3 desired properties here are satisfied. And this problem we can give to a QBF solver. The QBF solver can say yes or no.